right, Vera. Hello and welcome. I hear you're
Hey.
going to be talking about unboxing the Busybox. Can we talk a little bit? What is the Busybox? Well, first, who are you, Vera? Tell us your story, where
Uh,
you come from.
hey. So I'm a vulnerability researcher at Claroty, and today I'm going to talk to you about Busybox project, a research that we and my team conducted here in Claroty, along with Shahar Menashe from JFrog. The research was quite a success. We have discovered a lot of vulnerabilities that had been fixed. And the research, how we found it, how it had been fixed, the impacts on the community, it's all within the presentations that I'm going to talk about.
Fantastic. And where are you coming from in the world?
I'm from Israel.
Oh, excellent. Very cool. So it's over to you. Do you have slides for us today?
Yeah, I have
Okay.
slides.
I will leave it with you.
I will share. Okay. So everything fine? You can see
Yes, it
everything?
looks great. It looks great.
Great. So as I said, we are going to talk today about Busybox project, research that we done and Team 82 and Shahar Menashe from JFrog. So a little bit about myself. I'm Vera. I'm a vulnerability researcher at Claroty. Claroty is a cybersecurity company that provides visibility and security platform for industrial and medical devices. I heard some talks today about OT devices, and we have ICS challenge here at week 6, which is quite exciting. So I hope you know what I'm talking about. I'm a team 82. That's the name of a vulnerability research team within Claroty. Our main job is to pick a target, hack it, and disclose to the vendors the vulnerabilities that we have found. So the vendor will be able to patch those vulnerabilities and distribute them to the community. We as a vulnerability research team, like white hat hackers, believe very much at this job, and it is very meaningful for us. So I put here my Twitter handle. Feel free to reach out if you want. So let's go to the Busybox. So what is Busybox? So for everyone who not familiar with Busybox project, just think about fresh installed Linux distribution. We all know and we all familiar with our regular programs like ls, mkdir, mount, and so on. And there is a large number of them, and they all manage separately. And it turns out that embedded devices, those are devices that I was talking about, IT, IoT devices. The storage there, it's not that large as in general computer, and the use of those programs is not this extensive. So someone, and especially Bruce Burns, came up with the idea to put all of those executables in one sole binary. So by doing that, we have lowered the storage space of all the executables, now can be called applets, and we gave the vendor a strong tool. A vendor now can monitor and decide what executables can be opt out and thus not be within the device at all. So let's see how it looks like, how the execution looks like in a typical Linux machine. So just as you can see, instead of executing bin ls program with LA as an argument, we are executing Busybox program with LA as an argument. So it's basically the same things that done by two different programs. But that's pretty cool. Here we can see on the left actual embedded device and how it looks like within the device. So we see the listings of the bin directory. We see all the familiar executables as we would see in general computer. But here, instead of the actual executables, actual applets, we see only soft links. You cannot, I cannot hold it. But if you see on the left the arrow to the Busybox, it says that it's not an actual executable, but only a soft link to one in red, which is a real executable, and we can see that has a much larger size. On the right screen, we can see the main page of the Busybox, which states as the version and the compiled applets, the applets that vendor chose to compile and include within the device. So it turns out that almost every embedded device uses a Busybox within its file system, within its home router or IP camera. If the device is Linux-based, is probably running Busybox within it. And as we see in the wiki page that I have put there, Busybox is de facto standard for user space toolset. So I just hope that I have convinced you that research on that project is pretty meaningful for the community. And by fixing and finding the vulnerabilities in this project, it will have a great impact. So let's go again about the advantages of Busybox. So as I said earlier, it's pretty compact in size, about 2 megabytes for a whole toolset, compressed. It has centralized management. We have only one binary. We need only one binary to compile and to update, which is pretty convenient. And the most important tool in this day, I think, is the controls the vendor have on a tool set that he can easily opt out many of binaries application, and thus decreasing the attack vector for the device that, in which a Busybox is deployed. So the project is somewhat large, and we need to think about research methodology. And it turns out the code is open source. We can just review the code and search for vulnerabilities within the code. So I would like really briefly to list the vulnerabilities that we are security researchers, as the vulnerability researchers are look after vulnerabilities that can be exploited to, for further device compromise. So first is out-of-bound read and write, double free, user free, integer overflow and underflow, pass reversal vulnerabilities, null dereference, and more. I hope those are not very strange for you. Those who have a little experience in C programming should be familiar with those. So we have a couple of ways to research the project, and the first way is a manual approach. We are just going over the source code and looking for the vulnerabilities that I have described before. that's pretty laborious, and it's not the best approach for open source projects that takes a lot of input from the users. As we saw, Busybox is a utility that has arguments that are inputted by users, so we have a pretty large attack surface that we can explore. And the best approach for this is an automatic approach, and automatic approach for open source project is the best way to go to is with fuzzing. So what it means, I hope you probably heard about the technique. Instead of very similar to the unit test, when you just put some input and check whether the output is as you expected. Here we put a random input in a goal to crash the system. If the system is crashed, more often than not, it indicates the vulnerabilities that we discussed earlier. So fuzzing, as I mentioned, fuzzing is a utility with no knowledge about the system, which should be fuzzed. It tries to increase the code flows of the system by mutating the input. We will see how. And in the goal to crash the system, as I said, those crashes are monitored by the fuzzing ecosystem. And after the fuzzing procedure is done and the programmer looks at the results, he can go over all the crashes and fix the bugs within the system, which is pretty great. We chose a fuzzer that we chose is an AFL fuzzer, far most popular today. So as I said, I will repeat it briefly. Here is the main flow of the fuzzer. We will start with the choose the input. We will mutate it, so it will choose another path in our code, and we feed it to the target. Like in an example of Busybox LS, we will try Busybox LS and some instead of LS, we will try some other random input. We will try to mutate it to increase the coverage. And if the target is crashed, yay, we can save the crash and proceed to the next input. So AFL fuzzer is powerful. It detects vulnerabilities in some high-profile applications like PHP, OpenSSL, Firefox, and more. AFL is feedback-based. It means that it does not just send a random input. It sends an input and it tries to increase the coverage of the code flow based on that input, based on the path that had been discovered during the fuzzing. And the last but not least, AFL is the source code based fuzzer, which means that we need a source code provided for a project. Although AFL for binary fuzzing is supported, it's not AFL was not designed for it, and thus less effective. So let's come back to the Busybox. We will just now list all the steps we will do in order to fuzz the system. So first, we will write a harness of each applet of interest. We will write a simple code that will connect each of the applets that we want to fuzz, like some shell or a less applet, and we will we will write a code that will connect a nested in to the actual code that interprets the input. Usually we accept the arguments from the argument list and not the std. So that's something that should be tuned. It's really easy to write, and it doesn't take a lot of time. So the next we need to do is to compile the code with AFL compiler. It's separate compiler. AFL will insert its instructions without harming the logic of the system that compiled. So it will be pretty, it won't affect the logic at all. We will write a sample input just for something that a father can start with. It just can be a sample of how application, how a sample of input that application should get, and the father will by itself generate all random inputs upon this sample. We will run the AFL in controller agent manner, which means that we have one controller and multiple agents, and the more the better. We will pick agents as number of cores that we have on our system, and the more cores that are occupied with the father, the faster the father will go. We will stop the father when no new paths, no new code flows are discovered. That means that the mutation are not effective anymore, so we can stop the father. And after we stop the father, we need to triage all the results. We have hopefully a lot of crashes, and we need to pick all of crashes and create a number of unique ones, so we can start to work on the root cause for any crash that we have discovered. Just a little bit of how it looks like in practice. We decided to fuzz a couple of applications. I hope that you are familiar with some of those. Ash, awk, hash, man, and LZMA. Those are the applets that we fuzz with our father, and I have written the numbers that we need really to consider when we are fuzzing the main ones. So the first will be the speed of the father. It's the number on the left. The speed of the father is very important. If the father is too slow, it means that something wrong, and maybe you need to maybe the system goes through some unnecessary code, or maybe you can use a much better computer to fuzz the program, because if it's too slow, it just will take too much time. Another number is the number of code flows that are discovered. We want this number be increasing every time, and if this number is relatively small for a lot of time, it means that something wrong with our setup and we need to tune it up. And the most important, and the one that all father was intended for, is a number of crashes. When we see a crash within AFL, it means that AFL came up with an input that successfully crashed a system, which means that we have an vulnerability. So that's how our computer should look like when we are fuzzing. Just a pretty picture that I like to look at. So we fuzz our project, and we found a lot of crashes, 393 exactly. And that's a lot. It's not something that one can go manually and analyze every one of them. So we need a way to take all of those crashes and to understand what are the unique ones. And this procedure called triage. So AFL by itself provides a procedure that does and minifies the crashes, but we did something a little bit extensive than this. We wrote a simple Python code that will take an input and run the applet within GDB and just compare the stack traces of the crash. If the two stack traces are slightly different, it won't be assumed the same crash, and that's what we wanted to achieve. And thankfully, we went to 21 unique crashes within the system. So here we see two tables that are separated by the utility, and crash time. Crash type is just the CWE number. And those are vulnerabilities. Those are vulnerabilities that in some cases can be exploited further. And we weren't able to analyze them all, and we actually have only ones that is pretty easy to follow. And that's what we are going to do right now. We will take one crash of the manual binary. We will understand why the crash happened, and we will see how it was fixed. So let's start. I will put a little reminder for all of that, for all of us. Man is an interface that system manages just for manuals. And something that less known is that Man has sections within it. In fact, there is 9 sections within Man, and each program that we want to read manual about is put in some of these sections. For example, we have here the printf function, printf1 and printf3. When printf1 is a section that includes all the applets that can be run from the shell. When 3 is a section of libc functions. So printf1 is a function that you can write on your terminal, and printf3 is the one that you use in your C code. So it's the same name, but totally different functions. And we have manuals binaries that will show us the manual of function. Let's see how the man works. So it is really important for the vulnerability, but as a section is optional. It's not mandatory to use, but it is important in our case. So I showed here the use of a man with the section argument. So I hope you are all familiar with it. So if you want to read a manual of the ls binary, which resides in the first section, so what we do is just write man1 ls on the terminal, and we get the manuals. So as the next thing we need to do is to validate the crash. It can happen that the crashes are crashes are not logical and caused by some mistake, and we need to validate those. To do that, all we need to do is to look at the results of the AFL fuzzer, which is text files with an input that caused the crash. That's all. We take this and we feed a binary, the original one, not the one that was compiled with AFL fuzzer. We feed the original binary with this input, and this is a result. And as you can see in the lower image, we did cause a crash. There is a segmentation fault, which means that the system was crashed. So yay, that's a real crash. Let's analyze the code. The code, as I said, is open source. We can review it and find the real reason why it's happened. So let's take a little look. It's a middle of the function, and for everyone who is familiar with C syntax, it can be a little bit confusing, the argv notation. The argv here is already pointing to the second argument, to the one within 1, 1. So the first arrow that we see here is only, we want to ensure that this is the section name, that we have a section within a command. And we do the one is a section name. So we put one in our seclist and we advance the pointer. We advance the pointer to the next argument, which should be in a correct case ls, for example, or any other binary. But in our case, there is none. There is none arguments left. We proceed with the function, and in the third arrow, we can see is the strchr functions that reference the null pointer, and in programs with unmanaged memory, the program is crashed. So this is what happened. It was pretty easy to find, and that's why I chose it for this presentation. So I want to show you the results of this research. We can see for the media that it was important for the community, and the fixes that came a couple of months later were very useful to a lot of vendors. And I would like to take here a little note about what it means to find such a vulnerability, such crash within the system, why it is important. So think about any web server that can use some function within the device in its backend. And if the web server takes some input from the user and forwards it as is to this type of application, we get a crash, we get a denial of service in best case, and in remote coded execution in the worst case. So those vulnerabilities are pretty important, and we should work all together to find and fix them. And as programmers, we need to think about checking the pointers before referencing them. And that was the fix within the Busybox. We see that it was very simple. The only fix was just to ensure that the pointer exists. And just if it's not, we will just not proceed with the function and won't crash. So this is what a summary of our research, and I have some things to just summarized all the things that I have done. We have found 14 vulnerabilities with Busybox, and some vulnerabilities, not the ones that I have described, but some of them could potentially lead to the RCE. and Claroty have responsibly disclosed those to the Busybox maintainers, and they were fixed in a couple of months. Claroty have published a GitHub repository with all the harnesses and all the code that we developed during this research, and this code is available in this repository. So that's all. Thank you very much. Again, feel free to reach out. And that was my presentation.
So in this situation, do I congratulate you for finding a vulnerability? No, this is wonderful. It was a great presentation. I know we were quoting you on the Discord as well. I love it. Yay, system crashed. It's funny how we chat, right? Well, Vera, thank you so much for being here, and thank you for sharing really some detailed research with us in a tech talk around the Busybox and the vulnerability that you found. Thank you for everything you do for the community. We really appreciate it.
Just a little thing. It wasn't just my research. It was a cooperation with all my team. It's not only mine.
So kudos to the whole team.
Yeah. Thank you.
All right. We'll
Thank you. Bye.
Bye.